Hello and welcome to the Applied Thermodynamics lecture series. In the previous class we have covered vapor powered cycles. In today's class let us continue with this topic, and these are the topics which we are going to look at in today's class. We are going to look at the construction of saturation dome, different regions one can identify on a PV and TV plots when we take water as a working fluid, and then towards the end we are going to look at what is a criteria or a condition to find out the state or condition of a thermodynamic system. Let us briefly recall the contents which we have covered in the previous class. So in the previous class we have looked at a layout of a steam power plant as shown here. So here we have a layout which is comprising of different subsystems, and among these we have focused subsystem B for our analysis, which is basically composed of 4 important components. And we have seen that in this power plant water was used as a working fluid, therefore we call this as a steam power plant. And water being one of the pure substance, it is comparatively easy to analyze the system. Now let us look at different components which are comprising the subsystem B. So here we have 4 important components of a typical steam power plant. We have work developing device here, that is turbine, which produces shaft work, and section 1 to 2 indicates reversible adiabatic expansion process where work is extracted. Followed by we have a condenser, which is a kind of heat exchanger here, and the process from 2 to 3 signifies reversible and constant pressure heat rejection process. And we have the next component here, which is a pump, which is a work absorbing device, therefore we have the word in here, work input, whereas turbine is a work developing device, therefore we have work output. And the process that is taking place across the section 3 to 4 is a reversible adiabatic compression process, followed by the last component, that is boiler, in which a heat is added at a reversible and constant pressure condition. And we have the process 4 to 1 where heat is added at constant pressure condition. So this forms a cycle where working fluid goes through various phase change processes across each component which forms the steam power plant. Now let us look at the Rankine cycle, where in the last class we covered first about the Carnot cycle, and we have seen because of some practical issues or intricacies we are not able to proceed with a most efficient cycle, that is Carnot cycle for an heat engine. But however we found Rankine cycle to be the best suitable ideal cycle representing a steam power plant. So we have a Rankine cycle here. Process 1 to 2 signifies reversible adiabatic expansion process. It is an isentropic process along which we have entropy as a constant. And then we have process 2 to 3 where we have constant pressure heat rejection process. And then we have process 3 to 4 where we have reversible adiabatic compression process where pump input work is taking place. And then we have process 4 to 1 which signifies reversible constant pressure heat addition process. So we have 2 heat quantities here. One is heat is supplied from 4 to 1, the other one is heat is rejected from 2 to 3. Similarly, we have two work quantities here. One work quantity is from 1 to 2 where we have turbine work. The other work quantity is 3 to 4 where we have work input to the pump. Now with this background, when we apply steady force energy equation, steady flow energy equation across each components, that is the 4 components, we can arrive at the following work equations and the heat equations. So we have a work done by turbine, it's a specific work which is a per kg basis, which is given as H1 minus H2, followed by we have pump work where we made use of an property relation dH is equal to V into dP. Therefore we have dH comprising H4 minus H3, which is equal to V into dP, where V is the specific volume at a saturated liquid point, and then we have the pressure difference from pressure at a higher boiler pressure, and then we have pressure at the condenser. So this gives us work done by the pump, work input by the pump, where we have specific work input which is the per kg basis. Then we have an equation for heat input which is given as H1 minus H4. Similarly, we have a heat rejection process which is given as H2 minus H3 in kilojoule per kg basis. Now we have thermal efficiency equation which is net work divided by the heat supplied. So we substitute now the net work here is given as a turbine work minus the pump work. Therefore we have turbine work and the pump work, so we substitute turbine work minus pump work divided by the heat supplied, H1 minus H4. So this is an equation for thermal efficiency which we have seen, and H4 minus H3 represents pump work, and usually the pump work magnitude is much lesser as compared to the work that is developed by the turbine. Therefore most of the time the work input by the pump is neglected. In that case we are going to have only two quantities here, H1 minus H2 divided by H1 minus H4. So this forms the final thermal efficiency equation for a steam power plant by neglecting pump work. Now let us move forward, taking up saturation dome, and in the last class we have also seen the different performance relations where we had heat rate, steam rate, work ratio, back work ratio, and thermal efficiency equations. Now in order to compute all these performance relations, one has to find out the enthalpies associated at a different state points. To find out the enthalpies at a different state points, so there is a need for us to be clear about which kind of data has to be referred from the data tables. Therefore it becomes important for us to look at the construction of saturation dome and then identify different regions on the PV plot and TV plot, and then we will see the criterias which are used to find out the phase of the working fluid. So with this we'll proceed now. Let us now construct the saturation dome. So we have water here, so this is a system, closed system, where the water of 1 kg has been subjected to a pressure of 1 bar, which is atmospheric pressure, and initially the temperature of the water is 20 degrees Celsius, and it is piston cylinder assembly. So with this, as we go on adding heat to the system, there will be variation in the specific volume with reference to the temperature. Now let us plot temperature versus specific volume curve, and then let us identify different state points. So we have here a phase change process happening initially when the water is at 20 degrees Celsius. We locate the point as point number A on the curve, and then the pressure that is acting on the system is constant, but whereas the heat adding is varying. Therefore, as we go on adding heat to the system, heat that is absorbed here will be sensible heat, where we see there is an increase in the specific volume with increase in the temperature, and this process continues until a point is reached, and this point is called as saturation point, and the corresponding temperature is called as a saturation temperature, and the corresponding pressure, whatever we have here, is called as a saturation pressure. So this is a point at which water begins to boil. So from process A to 1, water was absorbing the heat. Now at state point 1, water begins to boil. So this is a boiling point of temperature. So we have a pressure here which is 1 bar atmospheric condition, and at 1 bar the boiling point of temperature is around 99.9 degrees Celsius, which is almost 100 degrees Celsius. So if we change the pressure, then the corresponding boiling point of the water also changes. Therefore, for 1 bar, the corresponding boiling point is 100 degrees Celsius. And as heat is continued to be added to the system, we see that without variation in the temperature, the curve behaves flat and it proceeds from point number 1, state point number 1 to state point number 2. So during this process, we see that a huge amount of heat is gained by the system, and this heat is utilized to convert the liquid into vapor. So therefore we have here latent heat of vaporization from process 1 to 2, and this is a process where we have dryness fraction which exists, which is also called as a quality. I'll come back to that point later. And as the system approaches state point 2, this is a point where all the liquid gets converted into vapor, and this is called as a dry saturated point. And at this point, if any further heat addition takes place into the system, there is a increase in the temperature. At the same time, there is an increase in the specific volume. So we understand that when the water is subjected to heating right from 20 degrees Celsius, so we see there is a different phase change which is taking place along A to 1, 1 to 2, and 2 to 3. So along this curve we see the pressure is constant. So this experiment is done considering pressure as 1 bar. So we have all the important phase change processes taking place. Similarly, if an experiment is performed by increasing the pressure, maybe around 30 bar example, then we follow a similar trend having curve as shown here, but the pressure now is different compared to the previous one. So we see that though the pattern is same compared to the first curve, we see that the width of the process from 1 to 2 is shortened in case of pressure P2 curve. So this shows that a huge amount of heat input has gone in converting the liquid into water. So it takes a very little amount of time for that conversion. Later on, if the experiment is continued with a much more higher pressure like 60 bar and so on, as an example, then we see the curve taking the following shape. So where P3 is much greater than P2 or much greater than P1. So in this case we see that as we increase the pressure and continue the heating process, we see the width of the process 1 to 2 keeps getting reduced. So more and more amount of heat is utilized in converting the liquid into vapor. So this happens in a very quick time now. So likewise, if we increase the pressure much more higher, then we can arrive at a curve as shown here. So this curve If we further look into this curve, then we see that we have one point which is coming up here. This point is called as a critical point. This point is called as a critical point. In the previous curves, we can see everywhere there are two points. One corresponds to saturated liquid point, the other point corresponds to dry saturated steam point or dry saturated vapor point. But with reference to curve D, or the highest pressure and temperature curve, we see that we don't have much distinction at this point where the slope becomes 0. So at this point, it's a point of interest here, which is called as a critical point, and the corresponding temperature is called as a critical temperature, denoted as TCR, and the corresponding pressure at this point through the curve is called as a critical pressure. And if we drop one perpendicular line and cut the x-axis, then we have critical specific volume. And the values for water, the critical point values for water is given here, which is 373.9 degrees Celsius, and the corresponding pressure is 22.06 megapascal, and the corresponding specific volume is 0.00515 meter cube per kg. So these are some of the important points to be remembered here. Further, if we go on drawing a curve passing through the saturated liquid points from each curve, then we get one half of the curve like this, and this curve is called as saturated liquid curve. The curve which is now formed by joining all the saturated liquid points forms saturated liquid curve. Similarly, when a curve is joining all the saturated vapor points, then we get saturated vapor curve. So here we have a dome. So this is how the dome is constructed, and in most of the textbooks we see a dome being presented, and one pressure line will be there or one temperature line will be there. So we see that by varying the pressures one can obtain this dome, or by varying the temperature one can also obtain this. So I'll come to that at a little later stage. Now if we get rid of the pressure curves and by retaining the curves, that is saturated vapor curve and saturated liquid curve, that is this dome, then same TS plot one can see that it appears like this. So we have the left part of the curve, which is called as a saturated liquid curve, and the right portion of the curve, which is called as a dry saturated vapor line, or it is called as saturated vapor curve. And the point here where we have at the peak is called as a critical point. And we can see that there are three distinct regions one can see on the TV plot. So we have a TV plot here. The portion which is on the left side of the dome, this region is called as a subcooled liquid region. So it is given here, subcooled liquid region. And the region which is within the dome is called as two-phase mixture region, or sometimes it is also called as a wet steam region. And the area or the region which is on the right side of the dome is called as superheated vapor region or steam region, which is shown here. So this is very important, that the left side of the portion of the dome on a TV diagram is called a subcooled liquid region. So we have on the y-axis temperature, and therefore we have a region here which is specified as subcooled liquid region. A similar way, when we perform an experiment, here in this case earlier we considered pressure to be constant and we went on varying the heat. Suppose if we keep the temperature constant and if we go on varying the pressure, in that case we are going to get the same dome as shown here, but here we have a PV diagram because pressure is keep on varying, and we have a temperature curve here which is kept constant. Just like in the previous case, in the TV diagram we had pressure which was held constant, but in case of PV plot we have temperature which is kept constant and pressure keep on varying. So again we see that we have three distinct regions here. The region on the left side of the dome is called as a compressed liquid region. So we on the y-axis we have a pressure, and this region is called as a compressed liquid region. Whereas in case of TV diagram, we on the region on the left side of the dome is called subcooled liquid region. So this is a basic difference between the TV plot and PV plot. However, the area within the curve is called as a steam point or steam wet region, or it is also called as two-phase mixture region, and the right side of the dome, that region is called as superheated vapor region. So we see that in TV plot and PV plot there is only one difference when it comes to the left region of the saturation dome. The other regions remain unchanged. And if one would like to know what is the state of the system when it is within the dome, then we have one parameter which is expressed here called as a dryness fraction, and the dryness fraction is given as a ratio of mass of vapor being produced from the total mass of the substance being supplied. Therefore, when we are in the saturated liquid point, for example at this point, we have x as 0. That means vapor is 0 and liquid is maximum. But as the process continues, we see slowly the steam formation takes place because of the latent heat of vaporization getting added, and it is converting the liquid to the vapor. And as it reaches to the midpoint, when the system reaches to the midpoint, we have quality taking 50%. That means among the total mass of fluid that is subjected, 50% of that liquid being converted into vapor. And as it approaches to the end point on the saturated vapor point, which is called as a dry saturated, at that point all the liquid is now converted into vapor point. Therefore it is called as a dry saturated vapor point. So these are some basics here for us. And moving further, in order to find out the state or the condition of a system, we have some criteria here lined up, and this criteria makes the things simple for us to know which part of the data table has to be referred under which condition. So if the given temperature, so in the system may be existing at some temperature, and that temperature is called as a given temperature. If it is greater than the saturation temperature, then we call it as a superheated vapor region. Then that particular region is lying in superheated vapor region. So one may have to refer to superheated tables to extract the property values. If the given temperature of the system is less than the saturation temperature, then the particular state of the system is lying in subcooled liquid region. So please remember that the word subcool comes when you are dealing with temperatures. Likewise, when we look at the TV plot, so we have a saturation dome here, and we have pressure being held constant, and saturation temperature corresponds to a horizontal line which has been extended and cuts the y-axis. So this is the point where water begins to boil. That is the saturation temperature. So the corresponding point gives us the saturation temperature. So likewise, when we are dealing with the pressures, so if the given pressure, which is a system pressure, been given to us, if it is greater than the saturation pressure, then the corresponding phase of the system is compressed liquid region. If the given pressure is less than the saturation pressure, then the state of the system is lying in superheated vapor region. Likewise, when we look at the PV plot, we have a saturation dome. So when we have a PV plot, temperature will be held constant. So this is a temperature, constant temperature line. And then we extend a line from the saturation point, then we get the corresponding point as the saturation pressure. So this is a saturation pressure, whereas a given pressure is something where the system is existing. Now with this information, and it will become very clear to us which part of the data book has to refer under which criteria or the conditions. Suppose if dryness fraction is defined, or if it is given in the problem, then it's simply straightforward, means that the system is lying in two-phase mixture region. So we know that dryness fraction is meaningful only when it is within the dome, only when it is within the dome. Therefore one has to refer to the two-phase mixture region saturated conditions. Then one can trace the values of pick up the values of corresponding specific volumes or enthalpy or entropy values. So in the next class we are going to take a few problems in order to apply the following conditions and then find out the state or condition of the given system. So with this we have come to the end of today's lecture. Thank you for your attention.